Hello there. So you might call this physics or you might call it differential equations, and it's fine either way for me. But we're going to solve a problem from electrodynamics. This is Griffiths' 4th edition, Intro to Electrodynamics. And we're solving the potential in this problem right here. Here's an example in the book, but I think it's a really good example to work through all of the details to understand it. And you kind of have to do that to really understand what's going on. So let's just get to it. We have this region in space in the xy direction. So this is the y direction, and this is the x direction, and it's bounded by these plates. So on this side, there's some potential function. We haven't said what that is yet. We're going to set it to something later. We haven't said what it is. And then on this x equals, or y equals 0 line, the potential is held to 0, and then at y equals a, it's held at 0. And then at infinity, it's 0. So we have 4 boundary conditions, okay? But we want to use those 4 boundary conditions to solve this equation. Let's just go ahead and write down those 4 boundary conditions. So here I have v, I want v of x and y. It's a 2-dimensional thing. So v of x is 0, y is this function v of y. I don't know what that is, but we'll figure that out later. I know that v when y is 0, so x 0 is 0, right? That's this boundary right here. I know that v of x a is 0. So when y is equal to a up here, we're at that potential that's also 0. And finally, I know v of infinity y is equal to 0. So if I get all the way over here, then the potential is 0. Now, this is clearly a 2-dimensional function, right? It depends on both x and y. So how do we do that? Well, first of all, let's write this Laplacian in Cartesian coordinates. This is clearly a Cartesian coordinate system because we're dealing with these, square things, rectangular things. So in Cartesian coordinates, the Laplacian is the second partial with respect to x plus the second part, is that still on the board? Yep. Plus the second partial with respect to y plus the second partial with respect to z. But we don't have a z coordinate here, so that's not a big deal. Now for the trick. This is called separation of variables. Let's assume that v of x and y can be written as a function, I'm going to call it f as a function of x and g as a function of y. The book calls this capital X as x, but see how that's dumb? I don't want to write that. Times capital Y, I don't know how you'd even write that. But then you're just going to confuse x and y, and so I'm going to use f and g. Is that okay? Okay. So let's put our function, I'm going to just write it f and g, although they are of x and y, into my Laplacian in my Laplace equation up here. So I have the second partial of fg with respect to x plus the second partial of fg with respect to y is equal to 0. There's no z component. I dropped that out. Well, right here, I have the partial of a product, but one of those products only depends on y, so I actually can pull that out. And right here, I have a product that only depends on x. The f only depends on x, so I can pull that out of my y derivative. So here I get g partial, second partial of f with respect to x plus f times the second partial of g with respect to y is equal to 0. And you may think, hey, we're still in the same boat. We still have 2 functions and 2 different derivatives, so that's a problem. Trick. There's a bunch of tricks here. Okay. Trick. I'm going to multiply both sides of the equation by 1 over fg. If I do this, this becomes, I'll write it out, g over fg, second partial of f with respect to x, plus f over fg, second partial of g with respect to y, equals 0 over fg, which is 0. Okay. So here, that cancels. That cancels. So now I have 1 over f partial of f. I'm going to write it up here, and a term that only depends on y. So now I'm in a nice position, very nice position. I have the following. I have 1 over f, the second partial of f with respect to x, plus 1 over g, the second partial of g, that's a g, with respect to y is equal to 0. Oh, that's a little high. I want it to be good. Let's erase it. 1 over f, second partial of f with respect to x, plus 1 over g, second partial of g with respect to y is equal to 0. That's better. Okay, now this term only depends on x. This term only depends on y. Now imagine that I change my x, but I keep my y constant. So this is gonna, the x's are gonna change here, but that stays the same. But still these two things have to add to 0. Or if I change my y, if I change my y value but keep x constant, well, they still have to add to 0, but this term doesn't depend on y, so it's not gonna change. So the only way to get this to work is to say this is equal to C1 plus C2, such that 1 over f, second partial of f with respect to x is equal to C1, and 1 over g, second partial of g with respect to y is equal to C2. They both have to be equal to a constant, right? That's the only way I can change the x's and still have it add to the y's and add it to 0. There's no other way. They have to be both equal to a constant. And C1 plus C2 is equal to 0, so C1 and C2 have to be negative of each other. That's the only way for it to work. Okay, so now let's pick values here. This is where you can make, again, once you solve a problem and it makes it messy and you go back and you say, hey, if I had done it this way, it wouldn't be so messy. So that's what we're gonna do. We already did it. I already solved the problem. Now I'm going back and I'm making it not messy, because otherwise it just gets blah. Okay, so because I've solved this problem already, I'm going to say, and you don't have to do this, just to make it less messy, I'm going to say C1 is some constant k squared. Why k squared? Who knows? You will see. And C2 is equal to negative k squared. Yep, that's what I want. Okay, I always get those backwards. If you picked just c and negative c, it would work. Okay. If you picked k and negative k, it would work. Why am I squaring them? You probably know why. Okay. That's fine if you don't. You're going to see. So now let's take just our x equation, just this one. I'm going to write this as 1 over f, second partial of f, with respect to x squared is equal to k squared, right? Because I said it's equal to that. Well, now let's multiply both sides by f, and I get the second partial of f with respect to x is equal to k squared times f. That's a differential equation. And it only depends on x, and that's cool. Now, if a differential equation only depends on x, can we solve that equation? Yeah. Well, how do you solve that equation? I can't integrate, right? Because I have this x and f, and it doesn't make it integratable. But I can guess an answer, and that's what you should do, right? That's the best way for physics to do. What function do I take the derivative with respect to x twice, and I get the same thing back with a constant in front of it? Well, here's a guess. F of x, I'll write it like that, is I'm going to write it as a times e to the kx. If I take the derivative of this, I'll just write it as f prime of x. It's going to be a k e to the kx. If I take the second derivative, f double prime of x, it's going to be a k squared e to the kx. That works. But wait, just like Yoda said, but wait, there is another. Or is that Ben? Well, I can't remember. But, so I can also say, if I put negative k e to the negative kx, I'd get a negative here, but then I'd get a positive right here, and it would still work. Right? So both of those work. So what we're going to do is to include both of those solutions. A e to the kx plus b e to the minus kx. So that is a solution to my differential equation for the x component. That's kind of important. Let's put it over here. So I have these boundary conditions. Now let's say f of x is a e to the kx plus b e to the negative kx. Yep, okay, I got that. Now let's do the same thing for this, right? So we already said that was equal to negative k squared for the y component. So if I multiply both sides by g, I get the second partial of g with respect to y is equal to negative k squared g. Does that look familiar? It's another differential equation and we're going to have to guess, but you've probably seen that before, right? This is a simple harmonic oscillator because this says I take the derivative, well, it's in space, not time. But if this was acceleration is negative k over m times x, that's a mass on a spring where we'd have k over m, not a big deal. But it's the same form of that. We see these forms again and again, and that's what's really nice about physics. We see these same kind of equations, so we don't have to resolve them every time. But we can go ahead and again guess a solution here. There's actually 3 ways you could write the solution, but let's write it in terms of trig functions. Okay, so what function do I take the derivative of twice and get the same function back with a negative sign? Sine and cosine both do that. So let's write g of y is equal to c sine k y plus d cosine ky. And let's just check, right? G prime of y, that's the derivative with respect to y, is going to be equal to, the derivative of sine is cosine, so I get c k cosine ky minus d k sine of ky. Am I off the board? No, I'm not. And then the second derivative, g prime of y, is going to be equal to c negative k squared sine of ky minus d k squared cosine ky. And so that is a solution because then I'd just pull out the negative k squared. There's a negative there too. Okay, so let's put that over here just for completeness. G of y is going to be equal to c sine ky plus d cosine ky. Oh, we're not done. No. We got a lot to do. Okay, so now that I have these, remember I had v of x and y was equal to g of x times f of y. Well, I have g of x, I have f of y, so that means this is going to be equal to a e to the kx plus b e to the negative kx times c sine ky plus d cosine ky. So that's my solution. But I don't know A, I don't know B, I don't know C, I don't know D. So I have 4 constants that I don't know, but look at this. I have 4 constraints, 4 boundary conditions that I can use. So we can apply those things. So let's just go ahead and start off with the boundary conditions. Let's start with this one right here. I know that when x goes to infinity, the potential goes to 0. So let's put v of infinity y. And this is not for math people. They're going to have a fit, right? But we're not math people. We use math. So that's fine. We can write that. So it's going to be a e to the k infinity plus b e to the negative k infinity times that stuff that doesn't depend on x. And I want this to be equal to 0. Well, this term goes to 0, right? So as e to the negative k infinity goes to 0, that's good. But that term doesn't. So the only way to make this term go to 0 is to say a is equal to 0. Right? That's the only way to make that work. So now my function, if a is equal to 0, I don't have that term. It looks a lot easier. That's why I didn't multiply this thing out. Right? Again, I knew what the answer was. If you'd multiply that out, it'd be okay, but I don't have that. So now I can write v of x and y. I'm going to write it as e to the negative kx times c sine of ky plus d cosine of ky. Now, you'd say, hey, what the heck happened to the b constant, right? Well, you can put b there, but b is just a constant. And so if I multiply the b through, I get bc, bd, that's a constant, that's a constant. I'm going to not call it bc, I'm just going to call it c, because that's what I had before. I'm going to call that d. It doesn't really matter. There's only two constants now. Okay. So I use this equation right here. Now let's use this equation right here. Let's say at y equals 0, v has to be equal to 0. So v of x 0 is equal to 0, and that's going to be e to the negative kx times c sine of 0 plus d cosine of 0. So now we get the same thing, right? This doesn't change with y, so I don't really care about it. But these terms have to go to 0. Well, sine of 0 is what? If you put it in your calculator, it's fine. It's 0. So this whole thing's 0. Cosine of 0 is 1. So in order to make the whole thing go to 0, I have to have d is equal to 0. So d is equal to 0. See how we're moving right along here. Okay, so now I have v of x y is equal to the e to the negative kx times c sine of ky. So we use that condition. Let's use this one right here. Let's say at y equals a, it has to be 0. So if I put that in, let's just go up here back to the top. So v of x a is equal to 0. And so that's going to be equal to e to the negative kx, x is just x, c sine of ka. Well, c can't be 0, right? If I put c is equal to 0, then it's just a boring solution, right? Everything's 0. It's always 0. That's dumb. Okay. So I have to make sine of ka 0. So sine of ka is equal to 0. And this is something that you see in your one-dimensional infinite square well in quantum mechanics. Well, how can I make this equal to 0? Well, this will be 0 if k is equal to n pi over a, where n is 1, 2, 3, and so forth. So I have to have a periodic value for k, right? There's multiple solutions where k is at. So that's important. I'm going to put that over here. K is n pi a. So just to check, right? If k is n pi over a, then it's going to be n times pi. When sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of 4 pi is 0, and so forth. So it could be any value of n, not 0, any value of n. Okay, so now we have values for k. So k is not constant. So that just kind of like set that, but we still need to know that c. So imagine that so imagine that I have n equals 1. Well, for n equals 1, I have v1 of ky is equal to e to the negative kx c1, I'll put it as c1, sine of, I'll put this as k1, this is k1. All right, for k1 is pi over a. Well, then I could have v2, e to the negative k2 x, c2 sine k2y. That's a solution too. Well, any value of n would be a solution. And so if I have all these functions that are solutions to my original equation, so remember we're back here, the Laplacian of v is equal to 0. Well, let's say v is equal to v1. Let's call this c1 v1 plus c2 v2 plus c3 v3, some constant. Well, then if I put that in here, I get the second, I'll just write this here, c1, the Laplacian of v1, plus c2, the Laplacian of v2, plus c3, the Laplacian of V3 equals what? Well, we already said that's 0 because it's a solution. That's 0 because it's a solution. That's 0 because it's a solution. So this is equal to 0. So that's still a solution. So in fact, the solution is going to be to add up all of these values, right? I need to know all of the values. So my total value, I already put the k over there. So my solution looks like this. V of x, y is going to be the sum over all n equals 1 to infinity, e to the negative k, and that has an n in there, I didn't put it in there, x, cn sine, I'll put it over here, n pi a, oh, y over a. So that's n pi over a. That's my solution. Now, I don't know the coefficient Cn. I still have to find Cn. Now, we're going to do another trick. So, back to the final condition over here. Let's write this. V0 of y is just some function. So V0y, if I put that in, I'm going to get k, x is 0, right? So this term's going to be just 1. So I have this is equal to the sum over n, I'll just put the sum over n, Cn sine n pi y over a. But that's also equal to this function v of y, right? That's whatever function I have on the boundary there, that's has to be equal to that. It has to be, okay? That was a boundary condition. Now we're going to do the trick. So the trick is this equation, I'm going to multiply both sides by sine of n prime, another n prime pi y over a, and integrate over all values of y. So I get this. I get, I can pull the Cn out front. It doesn't depend on y. The sum over n, Cn, the integral from y is 0 to a, right? Because it only exists from 0 to a, of sine n pi y over a times sine of n prime pi y over a. Remember, I multiply both sides by that, dy. And then on this side, I get the integral from 0 to a of v of y times sine of n prime pi y over a dy. So all I did was multiply by this sine n prime pi y over a and integrate from 0 to a. And then, but if I do that to one side, I'd have to do it to the other side, so I get two integrals. Now, the trick is over here, this integral is a fun integral, and I'm not going to integrate it for you. But this integral right here, the whole thing, is either equal to, is it a over 2? Yeah, a over 2. It is a over 2, right? Okay, I'm checking. Yeah. It's a over 2. It's sine squared. So, right, if you have sine squared from 0 to a, you get a over 2. Or if n is equal to n prime. So if I have 1 and 1 or 2 and 2, it doesn't really matter. I get a over 2. However, it's equal to 0 if n is not equal to n prime. So if this is 1 and 1, I get a over 2. 2 and 2, I get a over 2. 1 and 2, I get 0. 1 and 3, I get 0. Okay. So it's only non-zero if the n's are the same. So this whole integral is just going to be a over 2. This whole integral, we're just going to leave it. So that gives us the following. So this whole integral is a over 2, but I can write, oh, and now the only n that survives is Cn, right? It's just that 1, and I'm going to call that n2. So I get Cn is going to be equal to 2 over a, right? The a over 2 is over here, but I multiply both sides by 2 over a, times the integral from 0 to a, this is y is 0 to a, v of y, whatever that function is, sine of n pi y over a dy, right? Because the only one that survives is when n prime is equal to n, so that's where I get that. And so this is how we can find the value for every coefficient n, and we have to add up all those coefficients. So our total final solution, which I erased, I'm going to put it back up here, v of x, y is equal to, the sum over n, the sum, n equals 1 to infinity, Cn e to the negative kx, so, and that depends on n. I'll write it out the full way. E to the negative n pi x over a sine of n pi y over a. That's my full solution. But I have to find all the values of Cn. And there's an infinite number of Cn's, so you can't do it. But you can, because maybe you already see the hint here, but this is just like a Fourier series, right? When you want to represent a periodic function, this doesn't have to be periodic, but it does work the same. We can find the coefficients, Cn's, and multiply them by this trig function here to find the solution. Now, it turns out that the values of Cn's decrease with n number, so you don't. If I do the first 10, it'll work out just fine. Okay. Oh wait, we're not done. Okay. You may think, oh, I'm done with this. Bleep. And if you want to go and come back later, you know where I'm at. Okay, so you go do that. I know this is hard. You may have to watch this more than one time. But if you watch it more than one time, you should probably say, I'm going to subscribe and I'm going to do a thumbs up, which I've never said that before. I just want you to know that. So I didn't really say that now. And if you've made it this far, you deserve a thumbs up. Okay. So now from the book, from the Griffiths book, we're going to do the example v of y is some constant v0. And we want to find our values for Cn, and then we're going to plot it. Okay. So if I have that's true, I want to find my values of Cn. So Cn is going to be 2 over a, the integral from 0 to a, v0 sine n pi y over a dy. So that's just a constant. That's not a big deal. I can pull that out front. And then so what is the integral of sine? It's negative cosine. So I'm going to get Cn is going to be 2 v0 over a. And now let's just integrate this. I have to include the derivative of that stuff and then divide by that. So I'm actually going to get a over n pi negative, I'll put the negative there, cosine n pi y over a from 0 to a. So that wasn't so hard, right? Okay, now let's evaluate it at the limits. So these a's cancel. So I get negative 2 v0 over n pi. And then this is going to be equal to cosine of n pi a over a minus cosine of 0. And so we can leave it this way, and I'm going to just for the program. But you see here that if n is equal to 1, then this is going to be equal to cosine of pi is 0. No, cosine of pi is negative 1. So I get negative 1 minus 1, so it's negative 2. So I get, if n equals 1, I get 4 v0 over n pi. If n equals 2, I get cosine of 2 pi is equal to 1 minus 1, and I get 0. So if n is equal to 2, then Cn is C2 is equal to 0. Okay. So then the same thing going back over here. Oh, you can't even see that. Can you see? You can see that. Okay. So I don't want to erase that. So C1 is going to be equal to 4 v0 over 1 times pi. C2 is equal to 0, right? Because if I put in, you already saw that part. And then C3 would be v0, 4 v0 over 3 pi. and then C4 is equal to 0. Okay, but I'm going to leave it like this because that way I can just plug in whatever my value of n is, and I can write this as, I can write that as 1. And so sometimes this will be 0, and sometimes it won't. There's other ways you could do that. Okay, but that's that. So, but here you can see that as n increases, my c value decreases, so I don't need an infinite number of them. But let's go ahead and plot this whole thing out, right? So, of course, I'm going to have to make a 3D plot. I'm actually going to do a contour plot because I like that a lot better. And I'm going to need to have some values. So let's say V0 is equal to 1, A is equal to 1. That's fine. And we're going to go from x equals 0 to 2. Let's go to 1. Everything's 1. Okay. Now, in Python, I'm going to have to show you how to do this in real Python. WebVPython's not great at contour plots or 3D plots, so I'm going to use real Python. If you don't have it installed, you can go to Google Colab, and you can do this on Google Colab. I don't like Google Colab because it's infiltrated with AI, and it just makes me frustrated. Okay. So let's jump over to WebVPython. We got a bunch of stuff to do because we want to calculate these functions everywhere. But let's just do that. So here we go, making a plot. Okay, so starting from scratch. Let me get out my cheat sheet because I know I'm going to make a mistake. So the first thing I'm going to need to do is to import some stuff, right? Because I need some, this is real Python. So I'm going to come up here. I'm using Jupyter Notebook, so each one of these are little cells. Import numpy if you want, as in P, and then to, I should put in the same thing. And then to plot, I'm going to do import matplotlib.pyplot as plt. And then I have one other, and this is, I'll add it in later. I don't like the 3D surface plots because they're more complicated. The contour plot's a little bit easier. So now what I need to do is put my constants. So I'm going to say V0 is 1, A is 1. And I'm going to need to make my x and my y values. So let's make the x and the y values. So I'm going to say this, n is equal to 10. And then in NumPy, we have this function that generates arrays. So I can say x is equal to np.linspace, and I want to go from 0 to 1, and I want there to be n numbers. And let's just print that out and see what that looks like. I just want to show you. So here I have 0, 1, 0.11, 0.22, and so forth. And so you see that because I start and end at the numbers I picked, 0 and 1, then I don't have 10 things to split them up. So if I put this as n plus 1, you don't have to do this. But if I do that, now it runs out pretty nicely. So that's what I'm going to do. And now let's make our y values. Y is np.linspace from 0 to A, and we're going to have n plus 1. And we can always change that. And let's print y just to make sure it's okay. My y values. Okay, now I need to make what's called a mesh grid. So those are just my linear values, but I need a whole bunch of points. I need all the x's that go with all the different y's. So that's called a mesh grid. So we're going to do this. I am going to use capital and lowercase x and y here, and it's going to be an np.meshGrid. This one really took me a long time to understand. And what I'm going to give it are the values x and y. And then I'm going to go ahead and print x, just so you can see what it looks like. Capital X. So you see now I have a 2 by 2 list of numbers. And I could print out the y, and it looks different, but it's just rotated. So I have my x and y values. So that's really nice. Okay. Now what I want to do is to, let's call this, I'm going to call this nx. And I'm going to call this nx, just because I want to use n again later. Okay. And then run it. Oh, it didn't print anything. That's fine. Okay, so what I want to do now is to define how to calculate Cn. So I'm going to say, I'm going to make a function called C, surprisingly, and I'm going to pass to it a value nt, which is a temporary value. And now I'm just going to look over here on the board, and I have this thing right here. I'm going to just copy it exactly as it is. So this is going to be equal to negative 2 times V0 divided by n times pi. So it's going to be divided by nt times np dot pi. So pi is not a built-in function in Python. I'm going to use pi from the numpy module, which I called np up above. If you want to be cute and call numpy something else, import numpy as Bob, that's fine, but everyone calls it np. Okay, so you're gonna confuse yourself. And then I need to multiply by cosine, np dot cosine of nt dot times np dot pi minus cosine of 0, which is just 1. Okay, let's just try printing this out and see if it works. Print c of 1, and then let's do print c of 2. None. Oh, I didn't return. Return, let's just put it up here. Return. Okay, so it's negative 0, which is 0. That's fine. Okay, so but now any value of n I can have, I can print that. So what I'm going to do next is I want to add up my functions, right? For n equals 1, n equals 2, n equals 3, and so forth. And so to do that, I need to start off with a value function that I can add things to. So I'm going to make a potential function, a 2D potential function, and it's going to have zeros everywhere. And then I can add stuff to that. So I'm going to say v is equal to 0 times capital X times capital Y. So, and let's just print that. I want to show you what it looks like. Print v. So there it is. See, it's all zeros. So now when I calculate C1, I can add it to this, and I can add C2, I can add C3, and so forth. So let's say n is equal to 1, and I want to say n equals 10. I'm going to do this 10 times. And so some of these functions are going to be 0, and that's fine. So while n is less than n, what I want to do is to calculate v. So remember my function for v is v is equal to v, the old v, right, plus the whole function, which is right up here on the board. It's cn, so I'm going to say c of n times np dot exponential of negative n times np dot pi times x, capital X, divided by a. And then all that's going to be multiplied by np dot sine of n times np dot pi times y divided by a. And then I'm going to need to increase my value of n equals n plus 1, and let's print it again. It doesn't really make any sense for it here, but let's print it. So there's my stuff. Okay, so I don't really want to print it. I'm going to plot it. So let's make a contour plot. So the simplest contour plot looks like this. Oops. PLT dot contour f. I always misspell this. I need to give my x coordinates, which is capital X, my y coordinates, which is capital Y, and my v coordinates, which is v. And then let's put levels equals 20, and then that's it. And there you go. Okay, so notice that we have these little bumpy things at the beginning, but then it decays down, and it is 0 over here. Oh, we can put like this. Let's put this too. What's it called? There was one. You can put the, well, I don't have it on here. That's fine. You can put the bar on the side that tells you what the values of v are. I don't remember how to do that, and I don't want. I'm already looking at 39 minutes for this video. Let's go ahead and make the 3D plot, because that's what you want. And again, I don't understand everything on here, so I'm going to copy down what I did, because there's some stuff on here that just doesn't make sense. And the first one is this. I need to import something else from MPL tool kits .mplot 3D import axis 3D. 3D. Oh, and I got it wrong. From MPL toolkits. Okay, got that. And then down here, let's just put it down here. What I'm going to do is to say, I don't know why you have to do this figure. You got to do a figure. There's a whole bunch of really cool plotting you can do in Matplotlib, but I just don't get into it, to tell you the truth. PLT dot figure, and then I need to do ax equals fig add subplot. And some of the stuff you may not have to do. 1, 1, 1, that's just the angle that you're looking at it. Projection equals 3D. Oh, I don't think that matters, but 3D. And then ax.plot, surface. And then I do my x, y, and v. There we go. It's kind of cool. Kind of cool, but not 100% cool. Okay, but I want to show you, see this little squiggly thing right there? That's because as we increase the values of n, then we're getting closer and closer to a square wave. We're really doing a Fourier series for a square wave. So if I go up here and I did n is equal to 1, I can do 2 things. First, up here, I can increase my value of nx, which to 100, which it's not going to make that big of a difference. And if I replot this, see, it looks a little bit nicer, but I still get those squiggle things. What I need to do is have more values of n over here. So let's put this at 20. And then rerun this. And you can see it's coming closer and closer to being exactly what it was. In the book, in Griffiths, it said they did it at n equals 10. I don't think they did. I think they just said, just make that short. Let's just put this at n equals 50 and see if we can get it to work fine. That looks good. Pretty good. But I actually like this because you can see that we're not doing an infinite sum. And there you go. Whew. Okay, now we're done. If you made it through that whole thing, that's amazing. That I made it through that whole thing, I think is amazing for me too. But there is another way to solve this problem. We can do this numerically, sort of like what we did with the finite difference method. There is a way to do that. I'm probably going to make a video on that next. Obviously not here, but there you go. Talk to you later. Oh, the playlist for this whole thing is down below. Later.